Let's talk about the intrinsic conduction system or cardiac conduction system because we are conducting the electrical pathway of the heart for allow it to what we call depolarize, contraction, or repolarize, which is relaxation. Remember, it's a muscle, 3 types of muscle: cardiac, smooth, and skeletal. We're talking about cardiac muscle, referring to the myocardium layer. How do we get this tissue to contract? So we're going through the basic steps of this, and then what we'll talk about afterwards is what is this resulting graph when we look at the energy and the electrical impulses created from this, that we get an electrocardiogram. And we'll take a look at those points of the graph as a diagnostic tool. I also have a study guide for this to review everything that we've covered. So let's look at the intrinsic conduction system. I gave you a general pathway of how do we trace the steps through this, and then just the general organization of how do we process the electrical current that's going through the heart. It all starts at our pacemaker cells, and we see this in the right atrium. So the right atrium has what we call 2 nodal pathways. So it has an SA node at the top or superior part of the right atrium. This is called the sinoatrial node. And then we come down on the lower portion as we get to the medial side of the right atrium, which is the AV node or atrioventricular node. What are we talking about? So the nodal cells, these are what we call like automatic cells that can work independently to create that continuous electrical pathway for the heart so it can contract and relax basically on its own. Now, of course, there's influences from the external and internal environment that we get primarily from your brain, the nervous system, and then hormones that can control this, but it's still automatic by way of these special nodal cells. Your heart has to beat 3 billion times over your lifetime, so we want to make sure it's consistent. So when someone says that they had a pacemaker installed, what we're doing is to counteract and replace the problems associated with your natural pacemaker cells that you see in the right atrium. So as we go through this, sinoatrial node is essentially the primary pacemaker or the starting point. So it starts at depolarization. When we talk about that electrical impulse, it's going to start at the top of the right atrium. It's going to work its way down, and it goes through what we call internodal pathways that I don't have marked here, but we call the internodal pathways. And there's really 3 directional nodal pathways, but what it's doing is balancing the current as it's going to get down to the atrioventricular side. So that atrioventricular node will then fire afterwards, but that nodal pathway is creating a balance to coordinate it, but also give it time till we can get over to the left atrium, because we're going to essentially what we call contract all at once. The 2 atria contract, then the 2 ventricles contract. And we teach it like that, but it's not completely exact because there is a slight delay from the right atrium to the left atrium. But if we take this and count, this is all less than a second. This is extremely fast. So we go from our SA node down to our AV node, just a quick little slight delay, but then it runs across essentially our 2 atria contract. So we call that depolarization. And what are we doing? We are contracting the myocardium to push the blood down into our ventricles. So as we use this, we're relying on gravity and then also pressure. We talk about pressure quite a bit in anatomy and physiology. Pressure is a great way to easily move things, especially when we don't have to rely on energy. We can use the processes that our body creates just by pressure. So these are already actively filling, or passively filling is the better term for it. But the blood is coming down the ventricles, but we contract it, now we're pushing it down. So my 2 atria contract, and now we got to get the 2 ventricles to contract. So how we do that is go down the center of the heart. And what this center piece is called is the inner ventricular septum, in between the ventricles. So in between my 2 ventricles, I have the septum. To me, in simple terms, it's like the wiring coming down this interventricular septum. What I have here, and I listed in part 3 here, that I have what's called an AV bundle, atrioventricular bundle. So we're using that electrical impulse to come down, and that yellow wiring is describing that I'm going to go to the right side, atrioventricular, and the left side as I travel down the septum. I'm using this to create that depolarization that's going to come down. And our goal is to get to the bottom, which is the apex of the heart, because ultimately we want to contract and push up. Kind of like when you roll a toothpaste tube and you roll it from the bottom and squeeze it to get at the top so you can get it on your toothbrush. Kind of the same thing. We're getting to the apex to contract up and push the blood out of the heart from the superior side. So I come down from my two sides, the AV side, AV bundle, and what this is doing is getting smaller and smaller, we call Purkinje fibers. And you can't actually see this on this picture, but what I'm describing is once I get to the point where we travel down, it gets through these smaller fibers, Purkinje fibers, that are going to stimulate the myocardial cells or the myocytes when we get in there. So it's going to contract and push up. And as we're doing that, we're closing valves to prevent backflow. So our goal is ultimately, one, to contract the ventricles. What we also see in the right ventricle is what we call a moderator band. And this little band almost looks like a rubber band that's attached in there to help coordinate this, but it's also stimulating our papillary muscles, which are connected to our chordae tendineae, those tendinous cords to pull on valves to prevent backflow. So you have a lot going on there, but our goal is to stimulate the myocardium to then push this out. So very quickly, we go from SA node to AV node, cross over into the left atrium, full contraction. When we get the contractions of the atria, push the blood in the ventricles, the atria are going to relax, run down the interventricular septum by way of my AV bundles. So we go down our AV bundles, split to the right, split to the left. It gets smaller and smaller and becomes Purkinje fibers to stimulate that myocardium to create that depolarization or contraction of the muscles within the ventricles to push it up out of our valves. And where are we going through? Our pulmonary semilunar valve to go out to our lungs, and then are going out to our atrioventricular valve on the left side to go out to the body by way of the aorta. So as we do all of this continuous, I just did it 10 times just in that sentence. As I do this, I'm creating a graph, and let's expand on that. This graph is an electrocardiogram, ECG or EKG, and you often see this mostly in like movies and TV shows, and they'll show it on the screen that they flatline. So we're looking at these lines as it flattened, and if it's flattened, that's not a good thing. We need to revive you, in most cases with an AED, a defibrillator. But as we look at the process of this, we just talked about the ventricles and atria that are relaxing and contracting. When we get these waves, what we're describing is a diagnostic tool to analyze the heart and its rhythms based on what we see during these moments of time. So our first bump that we see is called the P wave. And that P wave is a result of atria depolarization, which means it's contracting. So the electrical impulse and the energy associated with that is giving me this wave here. So we have P wave from the atria contracting. Once they're done contracting, they're going to relax. During relaxation of the atria, we're going to have ventricular depolarization or contraction. That's our QRS complex. So this spike is a lot larger because the myocardium, the muscle activity, is a lot thicker in our ventricles, specifically our left ventricle, because it's got to pump to the entire body down to my big toe. So the QRS is a result of primarily ventricular contraction. Don't forget, we still have atria relaxation there. It's just we don't see it. It's like mass because of the ventricular contraction. So we have a result of this is primarily because of ventricles contracting. And then ventricles are going to relax. And so we have then that T wave. So that T wave is demonstrating the repolarization or relaxation of the ventricular cells. So we have this graph that's used this. Sometimes you'll see books or other texts that'll talk about a U wave after this. We don't fully understand a U wave at times, but it's contributing potentially to our Purkinje fibers and our papillary muscles. But typically we teach it as a P wave, a QRS, and then our T wave. So as we look at this, we're understanding that there's that electrical flow through the heart, but as a result, we can have a diagnostic tool to associate any illness or disease or any problems associated with the heart using electrocardiogram.